Thanks. Hello. Let's get started. Let's finish Fermionic today. Any questions from previous class? Yes.
Okay, last time in economic quantification, if you have a spin operator, we use anti-commutator, and then you said that if they have a Poisson bracket between spin operator and bosonic operator, then we use commutation relation. Is there any reasons we use commutation relation instead of anti-commutation relation?
Right. I guess there can be several ways of checking that. Good question. So the question is, last time we said, the way we quantize Fermi anti-commutator, boson commutator, and then Fermi boson commutator. So one way to check is that given Fermi being anti and then boson being a commutator, you can check what will be the consistent commutation relation you have to impose on the mixture. For instance, you can check, let me construct a boson out of the fermion bilinear. Right? And then since you know how to act on the Fermi by decomposing it, you can discover that, then you will be automatically appear to be commutator rather than anti-commutator. So for instance, there's a self-consistency you can check. Another physical argument we can make is that suppose I have an A boson and an A fermion. And then if I impose anti-commutator, then following the reasoning or discussion we had about the Fermi versus Bosch statistics, you'll find something weird. Okay. Obviously, in that case, you're not going to run into the exact paradox because there's no way that you can say, this one boson is really identical to the Fermi, so you will never hit the point where this state should be should follow the exclusion principle. But nevertheless, you see that there's some weird structure if you impose anti-commutator. But perhaps the best to check is, again, out of the Fermi, you can certainly construct the bilinears or product of four, or even any product of even fermion field, which are bosonic operators, and then you can just check for any of those cases, it should be a commutator rather than. Cool. Any other questions? All right. So let's continue and finish the Fermionic today. So last time we talked about the quantization, canonical quantization, and we more or less, sort of set it up all the prescriptions of what to do with it. So today, let's continue and talk about for instance, how we think about the F metrics, what is the Wick's theorem, how to construct the amplitude, how to compute the things using the Feynman rules, and so on and so forth. Okay, so we spent quite a bit of time last semester constructing those rules, imposing a lot of consistencies in how to think about those things. So today it will be quick because we sort of learn all of that, but nevertheless, there are a couple of moments where we have to be careful because we are dealing with a fermion as opposed to boson, okay, or scalar. So that's basically we were gonna point out a couple of things quickly. Before that, let me point out one thing. So basically, one thing that I want to just mention quickly is what happened to the causality. So previously we said, I want to quantize a Hermitian or real scalar field. And we say that, I have to impose this outside of the line because that's what a causality told me to do. And then we talked about the real scalar because then this is Hermitian. And since this is Hermitian, this is directly related to the observable. And so I know that any operator that can possibly be observable should commute outside of Lycon to be consistent with causality, right? That's what we talked about. So then we say, because that's the one part of the story we talked about. And then we say, okay, then we say we're going to impose, on the other hand, anti-commutator, which is 0 in general, but especially outside of Lycon. Okay. And we check that this is a good choice because then Hamiltonian is bounded from below, and then Fermi statistics work, and everything's good. But then if you compute this, right, then let's check, oh, now I want to check causality. Because causality means something has to commute outside of light. Meaning, if you measure one thing and then do the second one versus the other way around, there shouldn't be any statistical correlations. That's what it means to be totally factorized. But if you compute this, obviously this is like psi x, psi y minus psi y, psi x. But I know this is equal to minus of psi x, psi y, because I impose anti-commutator, then I get 2 times psi x, psi y, which is in general not 0. So if you're happy, we're done for this part of it. Okay, so what's going on, right? So that's the question. And the question is, this in a sense implies, but not necessarily logically, this implies that. So we learned that observables, therefore, very quickly should be associated with or related to permission operator in quantum mechanics. So that gives me a real eigenvalue and so on and so forth. We all know that. But in addition to that, we learned that, so observable, therefore, any operator that is getting constrained by causality constraint should be a bosonic permission operator. So that's how we learn. Okay. So for instance, suppose I have a system here. Okay. Suppose I prepare in the lab. I prepare a piece of vial semimeter. Okay, very good. So and then I want to do the measurement. There's a voltage, there is a current. I want to measure and check. It is one of the novel topological basal metal, and I really want to do that. Suppose I do that. And so one of my friends did that measurement. Okay, so I just have this tip, I measured the V and then I, and I was super excited. Okay, I discovered a new topological basal metal. And then this guy went around, walked around the once. Oh, I don't know. I'm just gonna walk around once. So this guy was observing this system using some operator, and this is walk around the once. Because he wanted to take a break. And then measured it again, all of a sudden everything comes out with a minus sign. We know that should never happen, right? So if this were Fermionic operator, we know that by definition, if you go around the once, you should pick up minus. And obviously you're gonna get a different answer. So this is another indication which is deeply related to this, right? Whether it's anti versus commutator, which is also related to whether it's a spin hat versus a spin integer. So we know this is not going to happen, it should not happen, right? And so we know that observable is bosonic permission operators. So this is not in contradiction, therefore. So therefore, whenever you construct a now observable operator, which is this to the given power, then again, it will check out that everything is causal according to this, according to that notion. Okay, so there's no paradox. Good. So I just want to make a quick comment about that. Any question about this? All right, so now let's move on. Now we're gonna basically redo what we have done for the scalar field theory perturbation. So the first thing to that direction is to figure out Wick's theorem. And probably you may have forgotten a lot of the details. So here is a list of equations you must have seen. So given a state in quantum mechanics, we know that there is a picture called interaction picture. And then interaction picture is related to the usual Schrödinger picture, as you are familiar with. And then we are in the system where there's total Hamiltonian, which can be factorized into something that I know very well, like a quadratic action, and then there's interaction, right? Small perturbations. And this is related by just rotation only by a H0. Good. And then we can also, then in this interaction picture, we can write time evolution in terms of some unitary operator, which eventually one of the most interesting objects we want to understand by this. And then we can check that this operator, so either you look at the time evolution of a state, or you can also look at the time evolution of the operator, depending on whether you want to do the Schrödinger versus Heisenberg type of picture. And last time we saw that this object, this operator, has to satisfy the following equation. So basically, this thing evolves according to usual looking equation. And so far, things look totally mundane. This is what you see in the quantum mechanics. The only difference being now that in this interaction picture in a given situation, and this Hamiltonian is called interaction picture interacting Hamiltonian. What that means is that starting out with the Schrödinger picture interaction Hamiltonian, we just rotate by, again, h naught. So that's how we construct it. So in terms of this looks very simple and nice. And then there was a formal solution to this equation. And the formal solution looked like almost just naive exponentiation. So the exponential of minus I, as you would have seen, and t to the t prime, t double prime, I don't do this. And then there's this interaction picture, interaction Hamiltonian integration. But then we saw that naive exponentiation doesn't work because this is now time dependent. Even if this is time independent, because of this mapping that connects the Schrödinger to the interaction picture, this is time independent. Whenever I have a time independent Hamiltonian, naively this doesn't make sense. So that was the moment where we invented what's called a time ordering. Then everything makes sense. Good. So with that, then what we did was, okay, now I want to understand scattering process. So starting from some in state, asymptotic state, and then I want to ask what's the overlap of that to the asymptotic future state. And then we say, oh, there is actually a nice way of writing this, which is I can still use the same basis, but I can imagine that there's a unitary map that connects between these two asymptotic bases. That was this S operator, and then S operator was given by basically interaction picture time evolution operator from time to the minus infinity to the plus infinity. This is a quick summary. And then whenever now I'm in a situation where I want to ask, here is the interaction point, and then there's some number of particles, P1 dot to the Pn, which is scattering into K1 dot to the Km, where this is time direction. Basically, what we are interested in computing is, given this external state, and then there's S operator, and then in state data. So basically now, this formula captures exactly how we can do the perturbation theory. Because now, if this is a small perturbation, I can expand this order by order, and then I can compute this object order by order in coupling constant expansion. Right? So that was the essence of a perturbation theory. Okay, now, basically, we want to run through all this quickly for the fermion. So which part has to be modified? So that's basically will be today's lecture. If there are any questions, happy to take. Okay, so good. All right, so then with that, hopefully reminding you enough about what we did last semester. Now let's actually talk about Wick's theorem quickly. Obviously, I'm not going to derive everything again, but I'm going to point out a couple of important differences. So to that end, in order to construct that, there was what's known as the Wick's theorem. So what was Wick's theorem? So here we already defined one notion of ordering, which is time ordering. And then there was another notion of ordering called normal ordering. So there's time ordering. Let me just write it in terms of scalar field for a second. And there was another notion of a ordering called a normal ordering. Right. So we're going to basically do the same thing for fermion. Time ordering is clear, right? So if time of x is bigger than that, I write it as phi s followed by phi y. If the time of y is bigger than this, then obviously I have to write the other way around. That's time ordering, literally. What was normal ordering? Well, scalar field had two physics. Also, fermion field has two physics. So one is positive frequency part, which is proportional to basically a annihilation operator multiplying positive frequency vector. And then this is negative frequency part, which has creation operator. And then again, polynomial factor capturing it is a negative frequency vector. So normal ordering was sending every annihilation to the right, all the creation to the left. Basically, if I put that into this, I want to see something that looks like all the creation operators sitting to the left of all the annihilation operators. So that was normal order. Okay? Why that's useful? As soon as you look at the expectation value, vacuum expectation value, that's immediately 0, right? So therefore, vacuum expectation value of all the normal ordering is 0. So that's a useful thing to invent. Then there was a notion of a contraction. So contraction was, what was the difference between these two? So in the case of a 2-point function, 2-point, we have a time ordering and then normal ordering. And then contraction was defined as the difference between these two, which we wrote as this. Okay? Good. And then we showed last time, not last time, many times ago, last semester, that explicit computation of this, which you should be able to do it real quickly now, is given by plus of x minus y when time of x is larger than this, plus y0 minus x, y of plus x minus. Okay, so that was what we found. And then another notation, so this, we invented another notation called delta of x minus y. And in terms of integral representation, that was given by 2e e to the minus it x minus. So this is basic, this entire board, if you like, is summarizing most of the concept we talked about. Okay, good. And crucially, contraction is what we need to write. Contraction is a C number because it's commutator, and commutator is the delta function, C number. Okay, so that was basically a lot of notions we went through, and hopefully you remember. And then Wick's theorem was given a chain of a time order product, and it's relating time order product to a normal order product. The answer was quickly. So first, it's a normal ordering of entire guy plus one contraction plus all one contraction plus then two all possible contractions, all two contractions, and so on and so forth. Until you get, if it is n is even, n over 2 contraction, meaning everything is contracted, or n minus 2 contraction, if it is the odd number contractions. That was the Wick's theorem. They're relating time ordering to normal ordering. Okay. What's useful? I mean, it's clear. If I take a vacuum expectation value on this side, any term that has uncontracted phase, that's trivially 0, right? So therefore, if you look at the equation, vacuum expectation value of the time ordering, then the only thing left over is complete contraction piece. Okay, so that's sort of thing. Good. Now, with that quick summary, let's talk about fermions. Okay. So let's talk about the fermions. There is just a couple of quick modification one has to do. Otherwise, most of the things survive and you can just keep it. So fermions, let's check. So let's consider a two fermion, psi of x. For now, let me just use psi of y, the same guy. Okay. So suppose I look at this. Then I'm going to write this as a psi of x and psi of y if x0 is greater than -2. Okay, good. Looks like that's a very sensible thing to do. And then for when y0 is greater than x0, because I'm supposed to time ordering, suppose I do this. Which also looks like a sensible thing to do. I just did a time ordering. Okay, now, and then since I know fermion has to be quantized with anti-commutator, remember now everything you see is not a classical field. This is operators, right? Ordering of operators. This I know should be equal to minus of psi of x, psi of y. So far, okay? So what I have written usually is naively. And let's check whether naive trial is good or not. Okay, so to that end, let's consider the following situation. So let me take a space-time. So here's a t, here's x. And then let me draw a light cone. Good. So here's my light cone. That's light cone. Good. And then this is therefore by definition light-like direction. Suppose I take another activity by either boosting or something, it will just contract and it will not change this light cone. Okay, causal structure will not be modified. Let me take another coordinate system. That. So this is going to be my u time, this is going to be my ux. Okay, good. So if I consider, so I'm going to consider two cases. One, I'm going to consider a point P that sits outside of light cone. So that sits outside of light cone, regardless of the frame you're taking. And the second time, I'm going to take a point which is a time-like. So I want to take a time-like point, which should be inside of the light cone here. So I'm going to pick a point here. Okay, so I'm going to consider 2 points. One outside of light cone, second inside of light cone. So one is a space-like separated, Q is time-like separated from a zero, the origin. Oh, okay, good. Now let's check the following. Good. So then let's look at the time ordering of psi of 0, psi of k. Okay, suppose I have one field inserted here, another field inserted there. Okay, then I'm gonna check time ordering. Good. Now this will become a check. If I look at the t comma x frame, where is it? T comma x frame, time of p is larger than time of origin. Yes? Okay, good. So then therefore let's continue to do what we did. Naively, I'm gonna write it as this. Right? So this is time order. On the other hand, if I am in this frame, now I'm in this t prime x prime frame, you see now this is the x. So p has a smaller time than origin. Okay, good. So now in this frame, I have to write it as this. Okay, so far I just followed naive prescription. Now, obviously, we know that this is equal to minus of psi 0 psi k, because this is anti-commutator. Good. So far I just did it according to the naive prescription. And what is wrong with this? What is wrong with this? If I say nothing is wrong with that, then cool, this is smooth. Something is wrong with this. P comma X prime and then T prime comma X prime is related by what? Lorentz transformation, right? This is Lorentz transformation. And then the answer here, one frame is what? Different from the other frame, which means the time ordering is not Lorentz invariant, right? So now you're going to compute a lot of time order correlation functions. That means that if you change the frame, looks like if I follow this prescription, you get a very different answer every time you change the frame. Exactly worst possible thing you can ever imagine, right? You don't want that. So we have to rectify. This time ordering is not Lorentz invariant. We have to make it Lorentz invariant. You can say what happened to the Q point here? You will see easily because now there's no problem, and even with my prescription, because this always has a bigger time than this, regardless of the frame. Okay, so you will get the same answer, but at least you have to make sure that things are Lorentz invariant in every frame. This prescription doesn't satisfy that. So the fix to this problem is the following. Whenever I started out with a given string of Fermionic operators, say these two, suppose I know now which time is larger than the other, and then I have to write in that form. Now, if what comes out of that is with the even permutation, meaning in this case I'm making a zero permutation, right? Then I write plus. If when I have to go into the form of a correct time ordered string through a odd number of permutation, by which I mean I have to make a one permutation in this example, then I have to pick -1 to the that much of permutation. In this case, 1. So therefore, cure to this problem is that I have to modify the notion of time ordering, including the usual kind of thing, but there should be a prefactor, which is -1 to the number of permutation you have to do to bring this given string into a form that you want to have, which is manifested time ordering. Okay, clear? So let me write a general equation for that. So therefore, for fermions, to have a Lorentz invariant time ordering, what we are saying is, suppose I have psi1 to psi n, and this should be -1 to the p psi, and called j1 to the psi j n, where time of j, this is manifested time ordering. So when you go from here to this string to that string, you have to do p permutations, for instance. So every time you have to swap two fermions, basically you have to take into account -1 thing here. Therefore, one corollary or immediate result of this definition is that if you look at the time ordering of psi of x, psi of y, this is obviously minus of time ordering of psi of y, psi of x. Because I have to swap, obviously I know I have to pick up the minus sign, which is consistent with the anti-commutator. And exactly for same token, we will modify the notion of a normal ordering too. So for instance, let's say I have psi1 to psi n normal ordering. Then again, there should be -1 to that p when you need to bring this guy to a normal order term. So now again, let me use the same notation, but meaning is very different. Now this is normal order. Normal. What do I mean by that? Let me make sure. So what that means is that all the creation operators, whatever, sits to the left of all the annihilation operators. Okay, so I might have to move around things so that on this side everything satisfies this normal ordering. And if I have to do p computation to do so, then I'm saying I have to pick -1. Let me demonstrate this quickly with just basically 2-point function, and then we can state the contraction.
Can I understand that inside the time ordering, the psi's are just Grassmann fields?
Yeah, yes, they are always Grassmann.
Always?
Or Grassmann variable or anti-commuting field. In this case, we are doing this as a quantum field operator. So yeah, they satisfy anti-commutator. So they always have to be consistent with anti-commutation relation. Any other question? All right, so let's check how this works for two-point function, and this will give us a chance to introduce a contraction for Fermionic. Okay. So to this end, let's take an example. So let me look at a first time ordering psi of x and some other field chi bar of y. And the reason why here I'm taking, instead of another psi of x, I'm taking chi bar, because it is this sort of combination, meaning one field, another field, derived adjoint, which will give us non-trivial information. Okay, Dirac propagator adjoint. So, I mean, this is clear because, this is clear because if x0 is greater than y0, I mean, this is basically, just write it as it is. And then in the other case, I have to flip. Now, so when I do that, I'm going to introduce one notational convention here, which will be useful and important. Now, recall that this guy has annihilation operator for the particle, and then profile for the particle, u, and then e to the minus plus whatever. And then this guy has a creation operator for the antiparticle, and then profile for the antiparticle, which is v. Right? Now, on the other hand, chi, which is a conjugation of that, will have annihilation for the antiparticle and the v bar profile for the antiparticle, and then creation for the particle and the u bar for the particle. Now, time ordering is about the time ordering. I think I said manifestly correct statement. Right? But so therefore, when we like drag things, move around, it's mostly about these operators. Okay? And then obviously, I mean, these operators. Because where this plus minus sign come from? I mean, where do we impose anti-commutation relations? We don't impose that on these C number functions. We impose that on these operators. So all the sign is relevant for the order of operators, not the order of functions, profile functions. Okay? However, it's crucial that this guy, for instance, will have, forgetting about a operator ordering, which is sorted out here. Basically, if I only focus on the particle case, this guy will have a U, and then this U bar structure. And you have seen that, if, for instance, if you sum over spin, this is like T slice plus M, by which I mean this is a 4x4 matrix. Okay? Now, let's look at here. If I naively imagine, this is a crucial point, if I naively imagine that I totally stop everything, then naively might say, oh, now this thing has a U bar U. Right? And this is a 1x1 Lorentz scalar, and this is a 4x4 matrix. That doesn't make any sense, right? So how come some operation changes something, a matrix to the number? So therefore, this should be avoided. So therefore, whenever I talk about ordering, I only mean that, literally operator changes order, but I'm not touching where this guy sits. Clear? So therefore, I demand that functions stay the exact same, only the creation analysis operator move around. So this will still have the same UU bar, for instance. And exactly the same thing for the normal ordering. Okay, good. So good. All right, so with that, let me now just write down the expression for the contraction. So contraction, psi of x, pi bar over y, contraction, is defined once again the same way, which is the difference of the time ordering and then normal ordering. And then by decomposing this field into psi of a plus, psi of minus, you know what I mean? This has annihilation U, creation B. Then I can also decompose this guy as plus and then minus, once again, annihilation part, equation part. You can literally write down time ordering piece and then normal ordering piece, making sure that there is this relative -1 to the P, both for the time ordering and normal ordering. You will find that this should be equal to when theta is equal to, so when time of x is larger than y, it should be given by this. And then y, when time is the other way around, instead you have, and then there's officially minus sign. For scalar case, you had a plus sign there, now it is minus sign. Because you changed order. So check. Oh, homework is up. Homework 1 is up on the website. Go and enjoy. Okay, and I forgot to say. Okay, so please go and check. So when this is just the algebraic but any questions so far? Yes.
그 스칼라 필드에서 전 뼈로인의 필드로 어떻게 그냥 커뮤니케이션에 따라서 그냥 마이너스가 지금 다 있는다는 거죠. 마이너스.
Yes. So yes, the question was about scalar versus fermion. The difference was in the case of scalar, this is just a plus, no matter what you do. In the case of fermion, depending on how many permutations you have to do to bring this string into that, you pick up this this minus to the p factor, both for the time ordering and then normal ordering. Okay, just to quickly demonstrate, probably this is too abstract equation. So here's a super quick demonstration. So let's look at the psi pi normal ordering, just to see exactly how it works. So how do you do that? First, you just write it as just to save a chalk. You mind if I write it as psi minus like that? So that I mean by superscript plus minus. Okay. And then there's a chi plus I minus. Okay, now this is annihilation. That's already normal order. So psi plus and plus, that's normal order. This is annihilation, this is creation. This is not normal order, right? So you have to swap. That means that when you do it, you have to pick minus sign. And then that is what? Creation knowledge, that's already normal order. So I don't have to do anything. Then creation created, that's also normal order. So I don't have to do anything. That's what I mean. So here, the only difference is that if you were scalar, I would have plus sign there, but because of fermion, I have minus sign there. That's all I mean. And because of this minus sign, when you take a difference, it will appear instead of a minus something, so you get commutator. Because of that minus cancel this, you get an anti-commutator in the conversion. Any other questions? Okay, good. So now let's compute the contraction. That's the Dirac propagator. So propagator is contraction. So because of this definition, you see that if I look at a psi x, psi bar y contraction, this is equal to vacuum expectation value of time order product. Because normal ordering gives you a trivial answer, right? With the vacuum expectation value. And this is the propagator by definition. And just to remind you very quickly, what happened for the scalar, so if you look at the scalar propagator, the answer, I'm just going to write down the answer, was overall d for p over 2 pi to the fourth basically so far Fourier transform, and then therefore what you might call a momentum space propagator at this form. So we have seen this, and then you had a one homework to work out right. And just to so that we're going to use that, this with the crucial epsilon I epsilon prescription in there, we can check that this is the same as actually 3D momentum integration instead of 4 over 2 times energy, and then into the same phase vector. Okay, so if you actually compute it, you get this. Basically, you have P minus, anyway, P0 minus energy, P0 plus energy. Because of that, you pick the right pole, you get this. So if you remember, that's great. If not, go back and check. Okay, so now let's quickly construct the Dirac propagator. So what do we need to do? Well, this is a propagator. I need to compute this. Okay, so let's do it. And there's some insight we can learn about it. So let's first consider x0 is greater than y0. Since I need to look at a time order product. Oh, by the way, you remember the form of the field, right? So the Fermionic field, to be precise, because you kind of keep track of factors. It looked like V 3E. In a normalization that I don't like, but nevertheless, let's do it. Otherwise, I have to change a lot of things. And we can do it. It's not a problem. So there's that. Not so happy normalization, but you can go back and then change the normalization. Sum over spin degree freedom, and then there's a profile function that has a 2 spin degree freedom with the momentum data, and then there's there's an annihilation operator for each spin degree freedom, which was for this case just x. Good. That's the particle, and then there were antiparticle bits, and then creation operator for antiparticle, and then it's negative frequency. So that was the quantum field for fermion, and then Shell imposed. I mean, it's not right. So that was that. So what we need to compute is, in this case, I need to pick up the case where now it's psi of x followed by psi bar y, right? That's time order. No minus sign because I haven't flipped anything. And then if you plug in that expression, what do you get? So in this case, let me just write that part and then we can read out pretty quickly. Fine. So here's the vacuum. So in order to get non-zero answer, what you have to get is that you have to pick a creation operator from this, right? And psi bar from that has creation operator part, which is b dagger u bar, and then e to the plus ip dot in this case y. And then since this guy hit the vacuum to the left, I have to pick up the annihilation operator. So that thing is b, as you see here, u e to the minus ip dot. Right? So starting out with a 2 momentum integral, and the 2 factors of that, 2 spin sum, and then you basically have a collection of modes. Okay, so if you do that, what you get is this. So let me just save some time. Write down. So yeah, if you do that, okay, you see how to do it, right? B, very good. Boom, so that I took care of everything. R and S, and then U from here. Remember, I said that I'm not gonna flip anything. R, U bar, S, E vector prime, and then there's a vacuum expectation which only acts on the operator, so it's a V, dagger. And then you can put R, S, V prime. Done. So I literally did it here. And then this is equal to anti-commutator minus B dagger B. But B dagger B is trivial. So basically same as anti-commutator, which is delta RS, delta momentum, delta. Okay? So that means that when you apply this guy over here, that gives you a projection operator or spin sum. And then since there's a one delta, one in momentum integral, one goes away. So finally you get D3P slash, because not slash, bar, because I just absorbed this together, over 2 energy. And then, oh, I forgot all the exponential factor. So e to the minus IP. I mean, effectively you get this. So e to the minus 5, e to the minus y. That's the answer. Oh, and then there's a this side. Done. Okay, so it's literally derivation. Okay, so that's cool. Now let's first understand the physics meaning of that and check whether that's sensible. And then we are gonna rewrite. What is the physics of this expression? What is the physics of this expression? So starting out with this 2-point function, and then if I put time over it. If I demand that time of x is larger than time of y, what it happens is that, remember, psi has a ability of giving you one or the other. It can give you a particle, or it can give you antiparticle. But it's not going to give you both simultaneously. Because one comes with the B, the other comes with the C dagger. So it's not going to give you simultaneously. So this is cool. The statement was that when this is the case, basically there's a propagation of a particle, not the antiparticle, from point Y to X. Now this is a particle propagation. So that is captured in here. So basically you're projecting onto the particle sector. Remember, this was a projection to the particle. And then nicely minus IP, which means that particle comes with a positive frequency, meaning sensible energy. And then now this time part is actually positive time, which means that it goes forward in time. Okay, so obviously I'm demanding that there's some propagation in forward in time, but what that means is that there's a particle carrying positive energy and going into that direction of time. So that's what this equation means to you. Okay. So now you can rewrite this equation as follows. Basically, I can bring it down P slash by taking a derivative acting on the x. Okay, so what that means is that this can be written as is acting on this. So M is literally the same. I haven't done anything basically. This is identity operator acting on it. And then if you add this guy, I cancels minus I, and then you take the derivative with respect to x, you bring it down P slash, that's exactly this. Okay? So this can be written as that. Now, what's the indication or implication of that expression? I told you that if, somehow you had some fictitious scalar field that satisfies this propagation, which is a unique propagator for relativistic scalar. But that was exactly the relativistic scalar propagator. So formally, whether you introduce that scalar in the theory or not, doesn't matter. Formally, Fermionic propagator can be written as, therefore, some fictitious scalar propagator by acting this operation. So that's the answer. I mean, this is literally formally writing it. Okay, this is not physical entity. If I only studied the Fermionic, this is an introduction of, if you like notation or mnemonics, I don't know what to say.
So that phi doesn't exist. Just exists just one.
Yeah, so this is ghost. No.
Just a
By both meant like really different thing. I meant
Yeah.
this is in your dream. Okay, and this is in reality. And you can just rewrite this way. Okay? Okay, good. So you can repeat the same exercise. You can repeat the same exercise in the other region of the time.
So then you can handle like electric field, like
Electric field.
not it is the psi bar is the physical one, and phi and v are physics one.
Yeah, auxiliary field. You just introduce so that there's a formal relationship.
So we can think the physical one as a field and the auxiliary one as a gauge field.
No.
Different.
No, yeah, so then, if you don't like this, pretend you never heard of it. That's also fine, okay? This has no much of content, okay? So last line, if you want, forget. Even this line, forget. This is good enough for me. Okay, now, what I could have done is the following on the other hand. Okay, probably I should have done that. Let's do it, so, okay? 5 minutes ago. So I was here. Cool. So you got all the physics interpretation, okay? And then you don't see anything here, literally. No. So then I can rewrite this as follows, okay? So here I'm going from here to there, okay? Since you can write this, okay. So 1 more minute spent. There, then what happens is this is still okay. So I'm not introducing any weird scalar field. So I'm just here. Go. E to the minus I dot x minus y. And then I told you that this is actually equivalent to this. Okay? So I'm just going to use that fact. Just mathematical identity, no physical entity, mathematical identity. So I'm just going to rewrite this as d4p and the Fourier transform of x minus y. And the p squared minus, since this is m, and m plus I epsilon I. Okay, good. Now let's actually impose this thing. So I'm just going to operate this guy instead of here, there, because they're identical. What do I get? The d4x into the minus I dot x minus y. And then if I do it, I will get I times p slash plus m. That's exactly what I invented the notation. The p squared minus m squared plus I. Okay. So therefore, the fermionic propagator. Well, for now, I'm just focusing on the one-time regime, but eventually this will be the answer. That this is basically Fourier transform of momentum space propagator of fermion. And so this will be called, I don't know, whatever you like. This is a momentum space of propagator from the Dirac fermion. Okay? So it's as if, because you're propagating, you want to have something like this. Remember? Because I want to have a pole, and then I know there's a particle with a mass m squared, Gordon, that's beautiful. But then I'm projecting onto the, if you like, particle sector, propagating particles. That's what's happening. Now, if you repeat the same calculation, but now if you do the other region, let me just take a fact. Now, if you do this, again, you do the same, keeping in mind that even if you see the time ordering like that, you never change the order of these functions, right? Remember that? You will see that in this case, instead of u bar, you will get a v bar. Therefore, instead of a VV dagger, you will get CC dagger. Instead, now you see that there is now propagation of antiparticle instead of particle, and then this spin sum give you p slash minus m. So, and you will get exactly e to the minus IP, and then y minus s, because that's the positive time direction, and p slash minus m. And parentheses over minus m, because you have to put it this order. Okay? So again, interpretation, well, you project to the antiparticle, positive energy carrying antiparticle propagating forward in time. Okay? Now, you can rewrite this because there's over and minus sign. You can change a variable to p to minus p to get rid of that. Then this turns into minus p slash minus m. There's over and minus sign. Get rid of it. Okay? So eventually, you will get the exact same expression. Let me say that again in 5 seconds. So far, that's the answer. I'm saying there's a minus sign, p slash minus m. But this expression is equal to that expression, which is manifestly invariant under p goes to minus p change of variable. Okay? So that means with one minus sign, and then instead of a p slash plus m, you have a p slash minus m. You can make a change of variable, p goes to minus p, you get this. And then combining with this minus sign, this turns into n p slash plus m. So that's a formal expression. Okay? And then you combine everything again, you arrive at the exact same expression. Yes?
I wonder why you don't define the propagator as psi bar psi?
Oh, the question is, why am I not defining good? Let's see what happens. If we look at the psi bar, so the question was, why we don't look at something like psi bar of x, psi of y? So that's the question. So in that case, let's see what happens. So this guy has what? So let's look at the particle vision. This thing has a creation operator of a C dagger V. This thing has a annihilation operator CV bar. For instance, I can look the other way around when we're looking at the particle case, not instead of antiparticle. Right? Good. So then this operator part will work out, I guess, the same way. There's nothing wrong, nothing different. So the only difference is that, this guy had a spin sum, this guy had a spin sum, and you seem to be getting V bar V instead of V bar. And this is a scalar rather than a matrix, 4x4 matrix. Now, you can ask physically, what's wrong with that? Good. Physically, what's wrong with this could be this. So if I have a single degree of freedom scalar particle, then what I should expect is that in this expression, the denominator is basically telling you what kind of mass particle is propagating. So this is data information about basically dispersion relation, or is that how you say? P squared is equal to m squared data. Relativistically, what kind of guy is propagating? Upstairs, on the other hand, is capturing, okay, are you shooting, single degree of freedom guy, 2 degree of freedom guy, 4 degree of freedom guy, and when it has a multiple degree of freedom, are they according to random internal symmetry connected together, or there's actually spin that connected them together? So this captures information about, internal degree of freedom space. So if I got, actually, it may be interesting to just actually compute and see what happens. But this seems to be getting just that with no information about spin, presumably. Or not, I don't know. Actually, I haven't done that check. Why I haven't done the check? Have I? Good. So in addition to 3 homework we already have, one of the student, tensor product versus direct product. So in the numbers, okay, so here is a good, nice homework problem that he will tell us about what's wrong with this. Very good. Any other question? That doesn't mean that you don't ask questions, okay? Another question.
저는 이 스칼라 빌드에서 기본하는 미적 관계가
Yes.
지금 나중에 좀 일반화될 수 있는 좀 좋은 트릭으로 쓸 수 있는.
Yeah, oftentimes one can write. So one thing that I can say is that this is sort of a generic form of propagator of spin to particle. There's a nice p squared minus m squared capturing dispersion relation, and then projection operator. If it is a spin 1 photon, you will see projection operator sitting here, which later after this basically we're gonna see that something like minus something like appearing on the numerator. So this is a projection operator onto the two polarization space of the photon, for instance. And also capturing why it is a photon rather than formula. Okay. The question was, is there a generic structure like this? Maybe true, because starting out with this, I think I can write down a projection operator acting on the exponential factor so that I can pull out this vector. Literally, I can write down box A minus something like that, right? Up to factors of I and something like here. So I think it is possible to write it this way. But you can do good physics without ever seeing this expression.
I have one question. So does that equation, t squared minus m squared, always works for composite fields as well?
Composite field as well, is that?
Yeah.
Yeah, so that's good. So the question was 1 over p squared minus m squared, that sort of expression. Is that true regardless? Or how general that statement is?
Yes.
Pretty general, because if I have any excitation, whether a fundamental particle, composite particle, like three guys, gathered together to become a single particle, doesn't matter. So long as they satisfy Clay-Fulton equation, which we talked about the fact that it should be the case. Okay, let me write exactly the function. How exactly should it be the same? Whatever, right? And any relativistic dispersion has to satisfy this at some point. And you see that this will be demanded by basically saying there's a Green's function you have to solve in the momentum space. And then to get the Green's function, this is literally Green's function actually. What you do is that you first go to the momentum space, which is the 1 over p squared minus m squared, and then you create a transfer of that. That's that.
So there's a statement unitary of the implication unitary that no propagators can travel decrease faster than p squared for 1.
Very good. There's that statement?
Yeah.
Good. So A, I already starting out with something manifestly good and unitary, but that's why I started with this. If you started seeing something fishy, like 1 over m to the force, blah, 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 there's a general non-perturbative statement one can make that such a thing is not unitary, as you try to say. And several ways to see. One way to see, okay, let me just construct what is known as a spectral representation. I mean, if somebody give me operator sensible, let me write down non-perturbatively, consistent expression of this sort. And at least this part is uniquely fixed. So we know this should be the case.
Okay, thank you.
Okay, moving on. The propagator done. Next, Feynman rules and so on. Before that, I'll just write down alternative expression, which is immediately. So let me hit this right here instead of starting on the U part. So you see that p squared minus m squared plus epsilon can be written as basically you look at this. What is what you have? M squared minus epsilon, right? I'm just pulling this part up. Okay, so what I'm saying is minus of m squared minus epsilon. And this is m minus I epsilon squared. Okay, up to linear order in epsilon. So what that means that I can rewrite this as a p slash minus m plus I epsilon, p slash plus m minus I epsilon. Okay, so this is p squared, the cross term vanishes, and you get that. Okay, and this commutes because gamma matrices, if you do it, commutes. So that means I can view this as this denominator as a product of this two formally, because this is a matrix, I mean inverse matrix. So therefore, this thing, Dirac propagator, can be written as I over p slash minus m plus I. And if you see it, it is nothing but this. So I am, this is Dirac Lagrange. If you pass on to the momentum space by looking at the positive frequency mode, this is nothing but p slash minus m psi. So propagator is, if you like, you'll see it eventually, basically is reciprocal of this two-point function. The same thing for scalar. Okay, so much for the propagator. Let's move on to the final rules. Okay, so let's now talk about final rules and scalings. So to this end, we're going to consider a simple theory. You call it theory, as it turns out, which has a scalar. In this case, I'm just going to consider real scalar, but in reality, actually, one can consider complex scalar. So on top of this free particle scalar, oh, this is bad. Free scalar with the mass mu, free Fermi Dirac Fermi with the mass m. I'm adding this interaction. So psi bar, gamma psi, scalar. That's the interaction. So what is gamma? So that depends on, we talked about 16 spinor bilinear. Okay, so if you were psi bar psi, when gamma equal to 1, we said that that's a Lorentz scalar. Then that means that this scalar phi should be a scalar as opposed to pseudoscalar. And then we also consider another object where this is I times gamma phi, I because now this is Hermitian. Then we show that this flips the sign under the parity transformation. Remember, parity is incorporated by gamma 0, and it anti-commutes except the minus sign. In this case, this should be pseudoscalar. In order for this theory to be parity invariant. More precisely, you might say, oh, what if in this case I pick a scalar? Am I something wrong? No. What really happens, which I think I mentioned several times, is that if you write down theory, it doesn't matter whether you recognize the good symmetry or not. This theory knows it. And the question is, given this assignment, what is the maximal symmetry that this theory enjoys? And the same theory is that if I pick this, you know, if I accidentally pick this to be scalar, I might say, oh, this theory is not parity invariant. But if you run a lot of experiments, you will get only data which are totally consistent with the parity invariance, because this will behave like pseudoscalar to be consistent with that. Okay, so there's always a symmetry in that sense for this theory. Okay, so this is what we're going to study. We're just going to look at a simple example process, and then from there we will learn a Feynman rules and how to compute them. Okay, so I'm going to call a particle that is created by psi to be a nucleon. So this guy creates a nucleon, N, following Coleman. And there's an antiparticle, which I call N1. And then phi, I'm just still going to call this phi, some random scalar excitation. So this particular interaction vertex describes there's a single scalar that meets with a pair of fermion. Okay, and then eventually we will start drawing this charge flow. I think we talked about it even when we talked about scalar already. Okay. So since we are here, let me remind you quickly. Given that charge flow, if I'm just stating because I already explained to you, if in this diagram, if momentum goes along the same direction as charge flow, then that means that this corresponds to a particle as opposed to being a antiparticle. On the other hand, if there is a diagram where the momentum direction is the opposite to the charge flow, then that corresponds actually to antiparticle. Okay, so we checked that last semester. So go back and check. So with that, let's look at the process. So let's look at the nucleon colliding with the scalar, coming up with the nucleon plus scalar. So the Feynman diagram we have to look at is this one. So there's a nucleon. Since I'm looking at the particle, I have to follow the charge flow. There's a scalar. So this is my notation for scalar. This is my nucleon. And the momentum goes along the direction of a charge flow. And then there's also momentum for this. And then the charge flow. So then this comes out with a momentum p prime. And this comes out with q prime. So it's q. And this, by momentum conservation, should be p plus q. Okay, so there's a very detailed discussion given in Coleman, which is great, actually. So eventually, you want to know how to compute this. And I told you the prescription. So what is the formal expression you have to write that is corresponding to this process? Well, I have to write this exactly as matrix equation. So I want to have a final state which has nucleon, which carries p prime, and then scalar, which carries this. And then I want to look at the S operator, and the nucleon with the p, scalar with the q. Is that what you want to compute? And then this S operator is nothing but a Dyson's formula. So this is time-ordered exponential of minus infinity to the infinity. Okay, so that's weird notation. No, it's not a weird notation. dt of this. Or, since you know that this Hamiltonian can be written as spatial integration over Hamiltonian density, which is more directly related to Lagrangian density that we are writing down. So this is basically time-order product of exponential of minus I entire, space and time, and then Hamiltonian density. So then the question is, okay, so this is a formal expression. I know how to set up the question, and how do I know that? How do I compute this? There's an algebraic way of computing it, operator algebra way of computing it by following Wick's theorem. And there's a final rule way of computing it, which is this mnemonics of how to do it. Okay. So good. Now, in algebra level, you can ask, okay, I'm going to expand this thing, but you already know at least order of a probability theory because I have at least 2 vertices here, right? So this is in second order in G. So there's one coupling here and another coupling here. So whatever this is, this diagram corresponds to a second order in the perturbation theory. I have to look at the expansion. So I have to look at the expansion, a second order in that. So 1/2 factorial. And then there's minus IG squared. So minus I comes from this minus I, and G comes from 8. Actually, yeah. I mean, if you do the Hamiltonian, there's a flip of sign, but anyway, that did I put I there? Let me make sure. And then there's a time ordering. I'm bringing it down 2 factors of an interacting Hamiltonian. That means there's time ordering psi bar, gamma, psi bar phi. There's one set, psi bar, gamma, psi bar phi, like second set. So let me just give the name 1, 1, 1, 2, 2, 2. By which I mean this is at x1, this is at x2. And then I forgot here. So here there's integration over p for x1, and then integration over p to x2. I'm literally bringing down 2 factors of that. So that's x1, x2. So 1, 2 labels the position space. And then the logical path to follow is that given time ordered product of chain or string of operators, then you ask yourself, okay, this will contain a lot of what? According to Wick's theorem, normal ordered products. And you can ask which of the contraction is relevant for this process. Well, contraction corresponds to the propagator. In this case, there is a propagator of fermion, right? From point, say, either 1 to 2 or 2 to 1, depending on which way you look at this. And fermion propagator, remember, has this structure. Okay, so for instance, if I want to have a fermion propagator going from the point 1 to the 2, I want to have 1, 2 contraction, right? And then if I want to have a fermion propagator from point 2 to 1, because I have a 2 thing, then I want to see a 2 to 1, right? So that's the contraction. So the first case is well, I have to contract that way. Okay, you might say, oh, that's not this order, but I told you, right? There's a contraction. You can flip order, that becomes that. There's a minus sign if you do that. The second case, you will have another normal ordering with that contraction. Okay? Let me say it again. Given time ordering, I'm not saying time ordering has a contraction. This, according to the Wick theorem, has a set of normal ordering with the contractions. And the contraction that is relevant for that particular process is there's normal ordering with either that contraction, there's another normal ordering with that contraction. That's what I'm saying. Good. So then I will leave you as a homework problem for the next set. Actually, compute this through the operator ordering, the exact normal ordering computation, given all these field expressions. And then you will find out that if you do it, this computation, you get the following answer. So first of all, there's a 1, trivial part, because if you extend the exponential, there's a 1, that one. Actually, let me say, I'm gonna look at this. So I want to just get rid of the trivial parts. And then you will get the following answer. So keep to 5 to the first delta p plus q minus p prime minus p prime. And then you will get minus ig squared, which we already anticipated. And then you get u bar p prime r gamma p q minus m. Ooh, I'm running out of space. Ooh. Epsilon. Continuing gamma, and then u p s. So if you actually do the calculation, both cases, you get the same answer, and you get this. Basically, either constructor will give you the identical answer that cancels this 1 over 2. Okay, and then you get this answer. Okay, so that looks whatever random expression for you for now, and then let me justify or let me explain the expression of this, and then we will extract the Feynman rules. So that's what I want to do. So first, this prefactor you'd expect, because if I prepare a momentum p and q and then momentum p prime q prime in the final state, whatever it happens, I don't care exactly what happens here for now, but whatever it happens, it should say some momentum conservation. So that means that there should be some factor telling me that that is identical to 0 unless momentum conservation is enforced. That's that. What about the rest? So this you would expect, because I know that that happens in second order. Good, that's done. And then you expect that because whenever one scalar meets with a pair of fermion, you have to have a minus I times g times gamma. And this can in principle be a matrix. Okay? So anytime that happens, there's a gamma here, there's another gamma there, and it is sandwiching this fermionic propagator. You'd expect that there is gamma, and then propagator gamma. And then it is a fermion propagator with the total momentum p plus q. So yeah, this is the correct Dirac propagator as we talked about. Okay, so far everything is expected. Very good. What about this factor? So let's just knock out this nothing. What about that? Well, let's look at here. Let's look at here. Oh, that's yes. Let's look at here. So then I'm sandwiching this chain with this initial and final state. So I mean, just to be clear, let me actually write down this part, but otherwise, I don't think I will make a clean explanation. So that's right. So what I have is following: nucleon with a p prime and something. I don't care of scalar for now. And then let's look at that chain. So psi bar, gamma, psi bar, scalar. I don't care for now. Gamma, I don't care. Let me just drop all of that. Psi bar, psi, nucleon with the momentum p. Because I just wanted to understand this last factor. Okay. So one of them is contracted. So let's just look at which contraction. Yes, let's just contract out this. Good. Okay. So that is a sort of a situation. What's happening here? So somehow somebody prepared the nucleon shooting in, and then it was coming, and disappearing at this point at x equals x1, right? And then something propagating, and then at x2, nucleon is created and then propagating to the infinity. So in order to have that, so initial state has that nucleon somebody prepared, and then coming in, and then if the situation were 1, 2, let's just consider this case 1, 2, then what happens is that this guy has to annihilate the nucleon, right? So physically, the nucleon comes in, it annihilated again, and then created at x2. That's the situation. So here I have to use a annihilation operator for nucleon with momentum p and possibly spin state. In this case, I call s. And then there's a propagation. That's exactly that propagator. And then at x2, this guy has to produce nucleon, and this guy has creation of a u bar with the momentum p prime, because that's the final state, and spin r. So you see, basically, therefore, I will have u r final state, momentum, and spin, u initial state, momentum, and spin, sandwiching propagator. So that's, you see what. Okay, there's a u bar, and then gamma we talked about, propagator gamma, and then u. Okay, so that's understandable. Now, let's just build up the mnemonics. So now what I'm going to do is that, given that we derived this, let's now define a final rule and then see if we can just write down this answer. Okay, so that's the goal. To this end, you remember that we define s minus 1 is equal to, so this is only non-trivial part. There's a momentum conserving delta function times I times what's known as matrix element. Okay, so that's how we define, because we expect that this should always be there, regardless. There's a universal factor, so we can factor out. So, and this is exactly the universal momentum conserving delta function we expect. So let's factor out. That means that I times matrix element is this object in the bracket. So this, by the right, in this bracket, square bracket is matrix element. Okay, so with that definition of a notation, now let's extract the Feynman rules. Feynman rules. Good. Let's clean up here a little bit. Then I'm gonna just use this. So for each vertex, so now this is the, I'm gonna say the Feynman rule. For each vertex, I will have minus IG gamma. Good. And then for the propagator, we know what to write down, so we write down the Fermionic propagator. Done. And according to the momentum. And crucially here, the momentum direction is the same as the charge flow. Okay, so it is this. Now, scalar guy basically, just like U plays the role of a profile, spin up and down profile, multiplying, plane wave vector. Scalar carries since 1 degree freedom, it's just 1 here. Okay, so that's why we only have this explanation. So this one has nothing, non-trivial thing we have to think about. And then the last thing that I want to say is that in order to sort it out, this U bar U thing, mnemonics is that you start out with end of arrow. So this is arrow, end of arrow, head of arrow, right? And then you run backward. Okay, you go backward. And then since this is a particle, I know I'm gonna have to write down U bar, go backward, and with the particle, I'm gonna write U. So that's mnemonics. In order to demonstrate what does this mean, let me write exactly another process. So now instead, when you look at this chart, this diagram, now I have a phi and bar goes in, phi and bar comes out, because now it's reversing the thing. So again, the same. So minus IG gamma, and then here, if I had a momentum K, in this case, momentum K reverses the arrow. So that means I'm going to have, instead of K slash minus M plus I epsilon, I will have a minus K slash. You might say, oh, I don't understand. Why minus? That looks like a total ad hoc rule. That's okay. It's ad hoc rule. No. So if I give you Q and then firm it up, by this I mean there's this error of a charge, there's a momentum Q. That was how we derived the Q slash minus M plus. Obviously, if somebody gives me reversed thing, this is compared to that, it's like sending Q to minus Q, right? Therefore, this should have minus Q slash. Not surprising, right? If you compare these two, this is a minus Q version of that thing. This is Q minus Q. Okay, so that. But then finally, about the spinner part. Now again, I'm gonna go from the head of the arrow and then to the tail of the arrow. So this is gonna reverse direction. Now I know this is anti-nucleon, so I'm gonna multiply V bar along the way, and then I'll end with V, but I have to write this order. So I'm attaching V bar and then V here. So now let's come back here, and then I'm gonna write an expression for that momentarily too. So what is the final amplitude? So I have these two factors, minus IG gamma, minus IG gamma. Here, let me just write down the answer. So I start out with the head of the arrow. What do I start with? U bar. Okay. My answer is U bar. But with what momentum? Well, P prime. And if I call the spin state of that thing is R, so that's what I do. Going backward, I hit this first. So I'm going to write minus IG gamma. I did it. And then I have a propagator, which is P slash Q slash minus M plus I epsilon I. And then I hit the vertex, which is minus IG gamma. And then I end with the nucleon tail, which is U. U of P S. So that is the answer. Let's repeat the same exercise with this process. So if I look at the now, and then I will end. And then I will end. Okay, so let's finish up this lecture with that calculation. Okay, so here's our now n bar plus phi goes to n bar plus phi process. And then let me assign the same momentum Q, E. So then K is P plus Q. And then again, P prime. Let me say that spin state here is S, here is R. I told you I start out with the head of the arrow, so I start out with this V bar. So my amplitude in this case, V bar with the momentum P, and then spin state S, done. In the following, I hit the vertex, which is minus IEG again. And then there's a propagator, but then since momentum is going against the charge, I know that it should be minus V slash minus Q slash, and then I1. Moving on, I hit another vertex, that gives minus IEG gamma. And then I end with the tail, that's V. So V with the momentum, K prime, and then the spin, R. So that's this. Okay. Yeah, so there's two more things I want to say about the fermion, and then we will switch to the gauge button. But today we will end here. Two more things: fermion loop, and then finally the spin sum. Okay, so and then we will switch to the gauge. Okay, so we'll finish here, and then I can take a few questions. Before that, yes.
뭐가 좀 있는데요?